Good afternoon, and welcome to the third of three videos on Chapter 5, which is all about measurements of variability. Now, today in this video, we're going to spend our time most of the time, going through an example of how to calculate these various uh, terms that we've been talking about over the last couple of videos. But before we do that, what I want to first point out is the strength of a relationship. All right. When you collect a data set, essentially, the data is stronger if most of the points in that data set are close together. In other words, if there's very little variability. The larger that variability, the weaker the relationship becomes. All right. So the strength of a relationship is determined by the variability of the dependent scores that are paired with each condition. All right. In other words, a strong relationship occurs when there is little variability among the scores, and a weak relationship occurs when there's a lot of variability amongst the scores. So, in other words, if all of the data is very close to the average of the data set, then it's a strong relationship. And there will be a very small variance number and a very small standard deviation number. On the other hand, if the variance number or the standard deviation numbers are very large, or larger anyway, then the relationship becomes weak, or at least weaker. All right. And so keep that in mind. All right. When you're looking at a set of data, the smaller the standard deviation value, the stronger the relationship is between the two variables that you're playing with. So why is this important? Well, how well a relationship helps us to predict the different y-scores is the extent that it explains or accounts for the variance in the y-scores. In other words, the closer the data is to the mean, in other words, the smaller the standard deviation, the smaller the variance values, the more likely there is that there's a strong relationship between the independent and dependent variables that you are measuring in your experiment. And so you're looking for a small standard deviation value. All right. Now, does that always happen? Of course not. Absolutely not. But the relationship itself is important in determining, inferring how strongly the data fit together and what kind of relationship exists there. All right. And so this is why calculating the standard deviation and the variance is an important thing to be able to do. Now, this is a data set that we've worked with before. All right. We use this to calculate several different things, especially when we were doing the frequency distribution stuff in chapters 1 and 2. But here, I'm going to ask you to use the following data set and find the range, the sample variance and standard deviation, the estimated population variance and standard deviation. All right, so we're going to look at the range, the sample, and the estimated population. Now, these are the same 18 data points that we used, but what I would like you to do at this point is to write them down in order, in a list. All right, so on a separate sheet of paper, get that piece of paper out right now and write down these 18 numbers in a list vertically along the edge of the paper. And I'll show you why in just a moment. All right, so I'm going to give you a minute to actually write these down. I know, thrilling video, isn't it? Okay, so if you look at this data set, you'll notice that the largest number is 17, and it appears only once. The next largest number is 15, and it appears 4 times. 14 appears 6 times. 13 appears 4 times. And then 12, 11, and 10 each appear 1 time apiece. Now, what that means is that we have a grand total of 18 numbers in our data set. So n equals 18. And if we wish to calculate the range of this, then all we have to do is subtract the lowest value from the highest value. So 17 minus 10 gives us a range of 7 for this particular data set. And so if we look at this here, all right, we've got the example range. The range is the largest value minus the smallest value. And so this is simply 17 minus 10 equals 7. All right, 17 minus 10 equals 7. And so for the data set that you saw in the previous slide, the range is 7. Easy peasy, right? And of course, range is probably the easiest of the measures of variability to actually calculate. But you have to be sure that you've identified the largest and the smallest data point. Okay. Now, in terms of calculating a sample variance or a sample standard deviation, we have to do a little bit more work. All right. And but whoops, I did this backwards. But before we do this, let's actually take our data and make a quick little chart. I know for a fact that n equals 18, so I'm going to write that down right here. And then I'm going to make a list of all of the x values. Now, I'm going to write them in order from highest to lowest. So I've got 17 appears once, then 15 appears 4 times, 3 and 4. Then 14 appears 6 times, 1, 2, 3, 4, 5, and 6. 13 appears 4 times. And then 12 appears once, 11 appears once, and 10 appears once. Now, what's important about this? Well, if I add up all of these numbers, all right, and again, get out your magic number box and add them all up. But what I'll find is that the sum of x is going to equal 246. Okay. Now, in another column, I'm going to write down all my x squared values. Well, it turns out that 17 squared is 289. 15 squared is 225. And I'm just going to put ditto marks here. 225, 225, and 225. 14 squared is 196. And that appears 6 times. So ditto, 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 and ditto. 13, come on now. 13 squared is 169. And that appears 4 times. 12 squared is 144. 11 squared is 121. And 10 squared is obviously 100. Now, if I then sum this column, so the sum of x squared, that if you, again, add all these up, so 289 plus 225 plus 225 plus 225 plus 225 plus 196, 196, 196, 196, 196, 196, 169, 169, 169, 169, 144, 121, and 100, you end up with a total of 3,406. Okay? Now, these two numbers, if you'll recall, are very important in the calculations of sample variance, sample standard deviation, estimated population variance, and estimated population standard deviation. So this is how we would calculate the sample variance. We'd use this formula. Again, notice we're using the capital S, and so that means we're dealing with the sample. This is going to be the sum of x squared, which we know is 3,406. This term here is the sum of x, which is 246, but we're going to square that, and then we're going to divide it by n, which I know is 18. Now, and then I'm going to divide the whole kit and caboodle by 18 again. So let's simplify this. Here you can see that I've plugged in all of the numbers. 3,406 minus the quantity 246 squared divided by 18, all divided by 18. And so that's going to give me a sample variance of 2.44. All right. Please take a moment, put this in your magic number box, and do the calculations. Make sure that you know how to use your calculators. All right. This will be important on your next quiz. Now, in order to calculate the sample standard deviation, it should simply be the square root of 2.44, right? Rather than reinventing the wheel, we can just do the same, use the same calculation and take the square root here. And so sample standard deviation is S, again, notice the capital, equals the square root of the sum of x squared minus the sum of x quantity squared divided by n all over n. And so we plug and chug. 3,406 minus 246 squared over 18 all over 18 is 2.44. And then if we take the square root of that, we end up with 1.56. Okay, so the sample variance and the sample standard deviation are calculated that way. Now, in order to calculate the estimated population variance and standard deviation, I do the same calculations again, only this time, rather than using n in the denominator of the fraction, I use degrees of freedom, n minus 1. Notice here, I've got the little s, all right, estimated population variance, and so that's the sum of x squared minus the sum of x quantity squared over n, all over n minus 1. Well, I know that the sum of x squared is 3,406, and that the sum of x quantity squared, well, the sum of x is 246, n is 18, and n minus 1 is 17. And so then the calculation comes out and works itself out to be 2.59. Now notice that this is a number that is bigger than the sample variance, right? The sample variance was 2.44, okay? But remember that the sample variance is always a biased estimate, and it usually underestimates the variance. And so since the sample variance is 2.44, and it's underestimated, it makes sense that the estimated population variance would be a little bit bigger. And 2.59 is certainly a little bit bigger than 2.44. In order to calculate the estimated population standard deviation, I simply take the square root of this number, and I get 1.61 as the estimated population standard deviation here. Now, this is, again, a little bit higher than the sample standard deviation, which was 1.56. And so, again, because the sample is an underestimation, we would expect that the estimated population calculation would be just a little bit bigger, and it is. We calculate this the same way. Little s is equal to the square root of the sum of x squared minus the sum of x quantity squared over n, all over n minus 1. So it's 3,406 minus 246 squared over 18, all over 17, and we take the square, and that gives us 2.59, like it did in the previous calculation. And then we take the square root of it, and we end up with the estimated population standard deviation as 1.61. Okay. So, my little friends, that is the end of the third of 3 videos on Chapter 5. Please make sure that you do the homework problems at the end of Chapter 5, and I hope that you learned something.